Hey everyone, welcome back. So today is a big day. We are officially tackling the sixth and final explainer in our WAVE series. Think of this as the ultimate boss level of your IGCSE Physics 0625 journey. We've spent the last 5 sessions really getting into the mechanics of waves. But today we are bringing the whole shebang together to conquer the electromagnetic spectrum. By the end of this explainer, not only are you going to deeply understand these invisible forces shaping our universe, but you'll know exactly what the Cambridge examiners want from you and how to nail their questions. Let's get into it. Here is our roadmap for this session. We'll meet the EM spectrum, cover its real-world uses, and look at the hidden dangers. Then we'll talk global communication, and finally, wrap up with an exam masterclass using real past paper questions.
All right, Section 1, meet the EM spectrum and its golden rule. We need to set up the absolute baseline for all these waves.
Okay, so the single most important thing to know is this exact number, 3.0 times 10 to the power of 8 meters per second. Put simply, that is 300 million meters a second. It's absolutely mind-blowing. Every single electromagnetic wave, from a giant radio wave to a tiny little gamma ray, travels at this exact same constant speed, in a vacuum. And actually, the syllabus notes that their speed in air is pretty much the same too. You've got to lock this golden rule into your brain right now, because I promise you, examiners love testing it.
But wait, if they all travel at the exact same speed, what makes a radio wave different from an X-ray? Well, it's their wavelength and frequency. To memorize the specific order the syllabus demands, we're going to use a mnemonic. Ready? Real monkeys insist very useful Xmas gifts. Look, I know it sounds a bit ridiculous, but trust me, this little sentence is going to be your secret weapon in the exam room.
Let's see how that unpacks. Real is for radio waves, monkeys for microwaves, insist for infrared, very for visible light, useful for ultraviolet, Xmas for X-rays, and gifts for gamma rays. Now, this specific list is arranged in order of decreasing wavelength. Radio waves at the top, they're massive, like 1,000 meters long. Gamma rays way down at the bottom, incredibly tiny. We're talking 10 to the power of negative 10 meters. And remember our golden rule about constant speed, because speed is constant, as that wavelength goes down the list, the frequency goes up.
Okay, moving on to Section 2, real-world uses. Let's open up the Applications Toolkit.
Cambridge doesn't just want you to memorize the waves, you have to know how we actually use them. Down on the lower energy end, radio and microwaves are the backbone of our TV and satellite networks. Infrared is your go-to for things like thermal imaging, while visible light is, well, it's how we see and take photos. As we cross into the higher frequencies, it gets pretty intense. Ultraviolet is used by shopkeepers to detect fake banknotes. X-rays literally see through our bodies for medical scanning, and gamma rays? They pack so much energy they're used to sterilize hospital equipment and even treat cancer. Memorize these specific pairings, guys. They are guaranteed easy marks.
All right, Section 3, dangers and harmful effects. We really need to understand the risks here.
Because as we push up that frequency and energy scale, the dangers seriously escalate. Microwaves can cause internal heating of body cells, literally the exact same way they heat up yesterday's leftovers in your kitchen. Infrared will primarily cause surface-level skin burns. Ultraviolet steps things up. Too much UV damages your surface cells and eyes, which can lead to skin cancer. And finally, X-rays and gamma rays. These are highly penetrating and ionizing. That means they can cause severe mutations or just outright destroy the fundamental cells deep inside your body.
Let's jump to Section 4, EM waves in communication. How does the EM spectrum connect the globe?
Okay, pay very close attention here, because examiners absolutely love trying to trick you on this specific point. For communicating with satellites out in space, we have to use microwaves. Why? Because microwaves punch right through the Earth's atmosphere to reach the satellite. Radio waves, on the other hand, actually bounce off a layer of the atmosphere called the ionosphere. So radio waves are fantastic for long-distance broadcasts that need to curve around the Earth, but they are totally useless for reaching space.
And speaking of space, you've got to know your satellites. Low Earth orbit, or LEO satellites, zoom around close to Earth, so you actually need a whole network of them to get continuous global phone coverage. Geostationary satellites, though, they are parked way up high, like 36,000 kilometers up, and they stay fixed above one single spot on the equator. That makes them perfect for satellite TV, because your dish on the roof just points in one permanent direction and never has to move.
Oh, and we definitely can't talk communication without mentioning optical fibers. These are the absolute backbone of your high-speed internet and cable TV. They use visible light or short wavelength infrared. The magic here is that the glass core of the fiber is 100% transparent to these specific waves. It allows huge chunks of data to travel massive distances by just bouncing off the inside of the cable. Total internal reflection, with practically zero signal loss. It's a total game changer.
All right, Section 5. The foundation is rock solid. Let's get into the exam masterclass and conquer some past papers. So, here is a real past paper question. The examiner gives you a block diagram of the spectrum, with missing regions labeled A, B, C, and D. You need a bulletproof way to identify them.
How do we crack it? We bring in the monkeys. Real monkeys insist, very useful, Xmas gifts. We see radio and microwaves are already filled in, so A, sitting right before visible light, has to be insist, infrared. Moving right past visible light, B is useful for ultraviolet. C is Xmas for X-rays, and D is gifts for gamma rays. Just like that, boom, 2 easy marks in the bag just from remembering one silly sentence.
Let's look at another one. Here, they're really testing if you understand the mathematical relationship between wavelength and frequency. Now remember, our mnemonic organizes waves by decreasing wavelength, right? But decreasing wavelength is the exact same thing as increasing frequency. So all we have to do is find the option that follows our standard mnemonic order from left to right. Let's scan. Checking option C. Infrared, insist, visible light, very, ultraviolet, useful, X-ray, Xmas. It perfectly follows the sequence. It hits the nail on the head. The correct answer is definitely C.
Okay, let's step it up to a trickier conceptual challenge. They want you to compare the speed and wavelength of visible light, X-rays, and microwaves in a vacuum. Where do we even start?
We start with a systematic breakdown. Step 1. Apply the golden rule. Every EM wave travels at the identical speed in a vacuum. So immediately scratch out options A and C because they claim one wave is faster than another. Nope. That leaves B and D. Now let's look at wavelength. Our mnemonic tells us X-rays are way further down the spectrum than visible light, which means they have a much shorter wavelength. So, statement D, in a vacuum, X-rays travel at the same speed as visible light and have a shorter wavelength, is the only completely factual statement. Answer is D. Last one. Let's tackle a classic application scenario. Which part of the spectrum sends television signals from a satellite to Earth? Think back to our communication deep dive. Microwaves are uniquely perfectly suited for this because they pass straight through the Earth's atmosphere without bouncing off the ionosphere like radio waves do. So the definitive answer is B, microwaves. You're going to see this exact concept tested time and time again for sure.
And that is a wrap on our masterclass. You now possess the exact toolkit, the rules, and the strategies to completely dominate the EM spectrum on your 0625 physics paper. You have officially beaten the final boss of our Wave series. But before we sign off, I want to leave you with something to chew on. We just talked about how microwaves pierce our atmosphere to talk to satellites. But as humanity pushes further and further out into the cosmos, how do you think we're going to adapt these invisible waves to keep communicating across the unimaginably vast distances of deep space? It's a wild thought. Keep wondering, keep studying hard, and I will catch you in the next explainer.